So you can also use tasks for recursive splitting. So here's a very simple example. What you do here is you want to compute the sum of an array. First you initialize the array with all ones, okay? So you say hash pragma OMP parallel, so multiple threads are going to get launched over here. And then one thread goes and calls sum equal to doSum. Okay? DoSum is a function which actually computes the sum of the elements. And this is the implementation of doSum. What does doSum look like? So what it's going to do is it's going to do recursive splitting. It's going to divide the array into half and create two tasks. One to compute the sum of the right hand side, one to compute the sum of the left hand side. So these are some boundary condition handling. Now here what it does is it computes the midpoint and it prints who's doing the summation. And finally it calls hash pragma OMP task here and assigns it the work from start to mid. And then it creates another task over here and it assigns it work from mid plus 1 to end. Seems simple? And finally it will say result is equal to x plus y. And that is what is returned over here. So there are several issues with this code. What is the issue? There should be a barrier before res is equal to x plus y. Okay. Anything else? What is the value of x at this point? Returned by the function. So the problem is that by default variables are treated as first private, which means a separate copy is created. Right? So at this point of time, for x, a separate copy has been created. And the moment this task gets completed, that copy is gone. That data is gone. It's not referring back to the same variable. Right? So that's the first bug. So if I actually run this code, what do I see? I see some garbage, right, as expected. So this is what I need to do. So I need to say here that x and y are both shared in these tasks. Now what will happen is, once this task is completed, when it sets the value of x, it's actually setting the value of the delegator, where it was called from. Right? And similarly this y is setting the value of the delegator, where it was called from. Now what is the problem? So now when you encounter res equal to x plus y, you are actually adding up these two values, but you've set them correctly from the tasks. So the shared issue is resolved. There's one more issue.
It has to wait for it to return.
It has to wait for those tasks to complete. The problem is that this thread is going to create this task here, and then carry on doing its work. It's not going to wait for them to complete. Right? Those tasks are spawned off, created. I don't know when they'll execute. So how do I know the value of x and y at this point of time? I have no idea what these values are, right? They are not filled from these function calls. So I need to wait for these tasks to complete. So how do I wait for these tasks to complete? I cannot use barrier, because what does a barrier do? A barrier waits for all the tasks across all the threads to complete. That's not what I want here.
Barrier for only tasks spawned from this.
Correct. I want to wait for all the tasks that are spawned, not by this thread also, which are spawned by this task. So when a task executes, it may spawn more tasks. I want those tasks to complete, and then I want to proceed further. Now what this is showing is that when I run this code, right, I still get the wrong result. This is a particular directive, hash pragma OMP task wait, which says that wait for all the tasks that have been spawned by this task so far to complete. So actually in OpenMP, when you encounter a parallel region, what you spawn is not 4 threads but 4 tasks. Okay, so we'll not get into that. At the top level, think of it as that either the set of tasks that have been spawned by this task, or if this is not a task but a thread at the top level, then all the tasks spawned by this thread, right? It waits for all of them to complete.
What is barrier?
So a barrier is going to be quite problematic over here. It's dangerous to use barrier inside tasks. Very, very dangerous. Suppose that you spawn 2 tasks. There are 4 threads, but only 2 tasks are spawned. Those 2 tasks call a barrier. They get stuck in the barrier. The other 2 threads don't even call a task. They go straight. There's no single barrier that all of them are encountering. They never even encounter a barrier. So you'll get stuck. There are other cases also. Even if all the threads were spawning tasks, how do you know how many tasks they were spawning? Or how many tasks they were executing? All the tasks may be executed by one thread, or 10 by one, 5 by another. But if you're calling a barrier inside that, how can you be sure that all the threads are going to call barrier equal number of times? You can't be sure about that. And if all the threads are not calling barrier equal number of times, then you are bound to get stuck. Your code will hang. So bottom line, use barrier carefully. There is a simple use case for barrier that in the main code, wait for all the tasks to finish. That's the way you should use it, right? Not to wait for some tasks to complete. That's very dangerous. Don't use it inside tasks. Barrier inside tasks is very dangerous. So the right call is # pragma OMP task wait. That waits for these to complete. Now, it's possible that after this I spawn more tasks and I again call # pragma OMP task wait, right? So within a task, I could call it multiple times. That's okay. But at this point of time, this thread is going to wait and it won't execute the remaining statements until these tasks are not done. That doesn't mean that this processor is going to be idle. It's going to put this aside and start looking for if there are any tasks that it can pick up. If there is any task it can pick up, it's going to start executing that. Yeah, so now if I execute the code, I see the correct result. That's what I expected. You have to be very careful with this. So let's go back to this slide. What is the danger here? I've said that X and Y are shared, which means that these tasks are pointing to these locations. Where are these locations? These are on the stack. This is a function. When are these going to get removed from the stack? When this function ends, right? And in this case, because I don't have a task wait, the moment you reach here and this function ends, this data is gone. This memory location is no longer valid. It may be used by some other function call or something else. Some other data could come on the stack over there, right? So that memory location does not belong to this X and Y anymore. So you have to be very careful when you're using shared inside tasks. That make sure that its scope is valid until the tasks complete.
So in this case, there is no implicit barrier at all.
Implicit barrier is associated with certain OMP directives. Here, this is a function call.
So you have a function which is calling a task and it's not even inside parallel.
No, remember? This is where we started.
Yeah, but how does the function know that it is inside?
Function doesn't need to know. You have to know as a programmer.
A task needs to be inside a parallel.
Yeah.
You can't spawn a task without a parallel.
Yeah.
So then the function must be telling the task, okay, this is a parallel.
That is something done at runtime. I mean, the compiler is going to replace that code with something. That may be accessing variables that were initialized at the time the parallel region started and so on. So you will run into trouble if you call that function from outside a parallel region. Then you'll run into trouble. But that will be a runtime error, not a compile time bug. At compile time, how does the compiler know? Compiler will just assume that this must be inside a parallel region. But it doesn't need to know which parallel region. You can invoke the same function from different parallel regions. What's the harm? Why can't I do the summation twice or thrice from different parallel regions? That's why it should not be associated with the parallel region. So remember that task wait is not a barrier, right? I hope that is clear. There is a difference between barrier and task wait. We've seen that barrier does not function as a task wait, but task wait also does not function as a barrier, right? And here's a simple example to see that. So here we have this no wait with hash pragma omp for, and I've said hash pragma omp task wait at the end of this for loop, right? And then I'm printing sum from hash pragma omp master. So only one thread is printing sum. So what's going to happen here? So in this case, what happens is in this particular run, if we see the output, so the master thread, thread 0, it came out, it encountered hash pragma omp task wait, but whatever it had spawned has already been computed. The tasks that it had spawned, they are completed. So it's going to proceed ahead and it's going to print sum. And you see that at that point of time, the value of sum is 300. It's not 600. Right? So just be careful about the difference between task wait and barrier, right?